PBL project for entitled Digital Electronic Clock. Me, Salin Ahmad bin Karim, matric number BS011 91014, Nurul Izzati binti Muhammad Jamil BS011 91012, and Muhammad Ashraf bin Harun BS011 91007. Okay, next slide. Okay, for my PBL, the problem statement is to reduce our time to justify the time is, but the ineffective clock makes this impossible. Second, been watching the clock for a while now, save the pattern of digit on its display minute by minute. Third, need to write down the same pattern many times. The solution must be consistent with all observation of the clock display, both in the first and following minutes. Then 3 might be various possible outcomes. Compile a list of all potential response in exceeding order of the time of day in that case. Last, still conceivable that the clock is not broken in the way that the problematic parts indicate. Okay, next. The objective of the project, first, to easy the people foresee the time when using the digital clock. Second, by employing simple 68K, you can save time, energy, and money. And the last, third, is creating a schematic diagram, stimulating the program, and running it on a 60K computer. Okay, next. The scope of the PBL project is for writing the code. To get the finalized one takes a lot of the time and work for our group. It is extremely complicated and difficult to comprehend. It is difficult to recall the syntax when my group try to do the programming. To run large assemble language application, the computer's size or memory must be increased and strong enough. Okay, next jadi. For the next slide is the methodology. First, it began a digital system and the use of outputs and timer interrupts. Button 1, it will display the increment status such as state equal 4. Button 2, then it will display status equal 1. Results, the increment house is 12, so it will be 0. This project requires an analysis of the results. Okay, next. This slide for digital clock coding using 60K program. So I want to run the coding. Share first lah. Okay. This is the coding for the digital clock. the table pointer and initialize set display. This is only need to be done the once. ORG start from 1000 for origin. So start using the LEA for lab counter A2, VAR A3 and index A4, then initialize display. Then for the second, you use LEA, move Q, and set the digit loop, move B, DBRA, using the transfer to D7, left clear. And then you use move Q to clear the long word using swap, move.w for copy time high word, clear.w for clear high word, move Q for 100 decimal, divu.w for divide high word, swipe for switch word, move.w for reminder back, and swipe for switch word back. The result in low word. Then divide the second to the value for the each digit. There is no need to do this word at a time, as the first divide can never cause an overflow. There are most only 10 of second in a day. So using LEA left for point to current time second, move Q for divide by 10 for second, BSR for digit, move Q for divide by 6 minutes, BSR for the digit, and then last move the V for save 10 seconds for hours digit. The current time is now divided into digit and saved to memory. Each digit is compared to the same digit the last time here, and if the differ, the digit is updated. At the first digit match, the loop exists as all remaining digits will be the same. So you use left, move the Q, compare, and BEQ for digit change exit loop. Use move the V for if else make last digit equal to new digit. Move Q for clear long word and get hours, minute, and second digit index. Okay. Use DBRA for loop if more digit to check, with bra for return to main loop. Okay, for extract the next digit value from the time, it's easy on the CCK as the divu. Instruction return both the result of divide and the reminder. In this case, the reminder is what we are interested in and in shape to the digit. The divided result is just pass back. So we use divu.w for divide for next digit. You swap for reminder into long word. Move.b for save time digit. Clear.w for clear reminder. Swap for return the remaining times. Okay. And then for end of code, digit index table, this is a simple way to map the SS, MSS for hour, minute, and second digit to the system clock digital. We use DCB.B for 10 hours, DCB.B for minute, and DCB.B also for the second. So all of the DCB powers by 0 to 5 lah. Okay, for variable, you use a lab underscore var for offset. Lab CURR for current time, second to 10 second hours. Use lab underscore loss for last time, second to 10 second hours. Okay. Let me start the digital clock program. So you click the button project, assemble source, and execute. And you can see the digital clock. The time is 00 hours 53 minutes and 55 seconds. The time is same with PC time, 12:24 a.m. The time is real time. Thank you. And my friend continue to.
Member. Okay, my name is Muhammad Ashraf bin Harun. I'm one of the part of the member. Now I want to show the result from my team. Okay, first you can see the first result, the positive edge trigger D. Okay, that means the output of the flip-flop represent the net value every time the clock signal travel from low to high. Each flip-flop, preset, and the clear input are all connect to the signal preset input and a single clear input. By setting all bit to 1, preset perform the counter to the greatest feasible value. By putting all the of the counter to the lowest possible value, clear set to the counter to the lowest possible value. To begin the counting, one of these input must be entered, as there will be no output state until one is set. Preset will set the counter to the value outside of the intent range. Therefore, clear is the best option to the start with. There also a second output called a carry, which will only show height when the count is 0. It is be used to the following module counter clock input. The count in the module 6, module 10, and module 12 is called the module 6 synchronous counter, and the module 10 call it synchronous counter. Alright. To the next slide. In order to perform the set non input was link the various preset and clear the crate at 12. The clock was made by connecting all this counter. This counter carry output become to this clock signal for the following counter. The clock goes from low to high when the 1 digit go from 9 to 0, and the following counter, for example, goes from 1 to 2. This pattern continues up the power digit. Alright, this is called the module 12 synchronized, and the top level design. The show, since they not record the clock functionally, the clear and preset input for the each counter were grounded. They clear input the minute and the second counter, as well as the set known input of the hour counter are used in the set known counter. When the set known control is high, the clock is set to the 12, and then the PM light is the final component to the design. Module 2 has a counter. When the preset and clear are both 0, like the toggle flip-flop, the clock signal in the module 2 counter from the lower to high whenever the hour digit change from the 11 to 12, and the light start change. The known of the count, the known was a control that allowed to set the time for noon. Scene was at 12 PM. The set noon control now connect the preset of the module counter. The module counter clear input is grounded. Okay, now I want pass to my friend. Okay, dah.
Okay, for the next slide, okay, discussion. To verify that each counter was counting the correct number. If it was not, it was usually due to a faulty equation or gate implementation reduced by allowing the clock to run and ensuring that 9 become to 10:49 became 15 and 15:9 became once. Okay, speed up, move the pulse generator around to different portions of the counter. This procedure includes the use of the PM light. Okay, and the next slide is a conclusion. Okay. In conclusion, the digital clock system was designed with EZ68K. It can be simply reprogrammed to get required result. Troubleshooting, procedure, programming, and dealing with EZ68K. The system presented in the report can be enhanced with several aspects like as the time and alarm setting. Okay lah, aku dah mau gugur.